We spend a lot of time in math classes graphing functions, learning to recognize the graphs of basic functions, and analyzing the graphs of functions. Obviously, graphs must be useful. This video discusses some of the information that can be gleaned from the graph of a function. We will start with a basic overview of topics to be discussed. Intercepts. Recall that intercepts are points at which a graph intersects an axis. An x-intercept has the form a, 0 and is a point on the x-axis. A y-intercept has the form 0, b and is a point on the y-axis. Domain and range. The domain of a function is the set of x values or first coordinates used in the function, and the range is the set of y values or second coordinates used in the functions. We'll also discuss intervals of increase or decrease. These are domain intervals over which the function values increase or decrease. Local or relative extrema. Extrema refers to maximum or minimum function values. Local refers to a specific interval in the domain. For example, local extreme values occur at the top of a hill or the bottom of a valley. Local extreme values are sometimes called relative extreme values. Absolute extrema. Absolute extreme values are exactly what the name implies, the biggest or smallest function value over the entire domain. Note that absolute extrema are also called global extrema in some texts. We will give both examples of these graphical features as well as precise mathematical definitions of them. Consider the given graph. We can identify the intercepts by locating where the graph intersects an axis. In this case, we have 3 x-intercepts, and the origin is also the y-intercept. We can identify the domain of the function by observing which x values are used in the graph. We have to interpret from the arrows on the ends of the graph that the function continues for all real x values. Similarly, we can identify the range of the function by observing which y values are used in the graph. Again, we interpret from the arrows on the ends of the graph that the function continues for all real values. Intercepts, domain, and range are topics we've covered in previous videos. Let's consider the other topics. Informally, the function is increasing where the graph is rising, and it's decreasing where the graph is falling. It's very important here that we are reading the graph as x increases from left to right. When discussing intervals of increase or decrease, what we actually specify is the domain intervals over which the function increases or decreases. In this example, the function increases on the open interval from -infinity to -2, union the open interval from 2 to infinity. And the function decreases on the open interval from -2 to 2. Note that intervals of increase and decrease are always open intervals in the domain of the function. Local maximum occurs at points where the function changes from increasing to decreasing. In this example, there is a local maximum of 16 occurring at x = 2. Importantly, the maximum function value is the y value. Similarly, local minimums occur at points where a function changes from decreasing to increasing. Here there's a local minimum of -16 occurring at x = 2. Note that in this example there is no absolute maximum nor absolute minimum because the range of the function is all real numbers from -infinity to +infinity. It's worth discussing the mathematical definitions for these concepts. Mathematicians use a very precise and particular language to ensure that there is no room for misinterpretation of the concepts. Learning to read and interpret this language is essential to understanding mathematics. We will start with definitions of increasing and decreasing functions. A function f is increasing on an open interval, provided that for every a less than b in the interval, f of b is greater than f of a. This is the mathematical way of saying that as you read the graph from left to right, the function values get bigger. Similarly, a function is decreasing on an open interval, provided that for every a less than b in the interval, f of b is less than f of a. This essentially says that as you read the graph, still from left to right, the function values get smaller. It's important to note that in both these definitions, we are considering what happens to the function values as we read the graph from left to right. Let's continue with more mathematical definitions. Extreme values are essentially those function values larger than or smaller than all other function values. But let's be specific. A function f has a local or relative maximum at the point a in an open interval, provided that f of a is greater than or equal to f of x for all x in the open interval. So essentially, f of a is the biggest output over the interval. Similarly, a function f has a local or relative minimum at a point b in an open interval, provided that f of b is less than or equal to f of x for all x in the open interval. Thus, f of b is the smallest function value on the interval. The absolute or global maximum of a function is a value f of c, provided that f of c is greater than or equal to f of x for all x in the domain of f. So f of c is the biggest output over the entire domain. Compare this to 1, where we're looking at f of a being the biggest function value on some interval. For an absolute maximum, f of c has to be the biggest function value over the whole domain. The absolute or global minimum of the function is a value f of d, provided that f of d is less than or equal to f of x for all x in the domain of f. Thus, f of d is the smallest function value on the entire domain. Again, we'd like to reiterate that if a point p, f of p corresponds to an extreme value, local or absolute, the extreme value is the function value f of p, and it occurs at x equal p. Let's consider a final example in which we are given the graph of a function y equal f of x, and we identify the graphical properties we've discussed today. We have a function y equal f of x defined by the given graph. The intervals of increase are the x intervals over which the function rises. Our function is increasing on the interval from -1 to a half, union the interval from 1 to infinity. The intervals of decrease are the x intervals over which the function falls. So our function is decreasing on the interval from -infinity to -1, union the interval from a half to 1. We have turning points at x equal -1, 1/2, and 1. Turning points describe all places where the graph turns from increasing to decreasing or decreasing to increasing. These are collectively where our local extreme values occur. In fact, we have local minimums at x equal plus or minus 1, and a local maximum at x equal a half. We have an absolute minimum at x equal negative 1, but we have no absolute maximum as the function values are unbounded above. We should also mention that although the graphical features we've discussed are often identifiable with a good graph, to find these features analytically requires calculus for most functions. In some special cases, like parabolas, we can and will learn to identify the features using algebra. In other cases, we will utilize good graphs.